Hey, I'm Derek. After running on an AMD Ryzen AI NPU, I discovered something that the official guides completely missed. Most NPU optimization content is vague. Mine isn't. This is my exact process for achieving up to 100% NPU utilization on the HP OmniBook 3. It's tested, reproducible, and it works. The test hardware: HP OmniBook 3 Ryzen AI 5 processor and 16 gigabytes of RAM. I developed this protocol using FastFlowLM, Lemonade Server, and Gaia CLI. Why does this matter? Because every optimization guide treats hardware like it's infinite. It's not. Your constraints are specific. Mine are 16 gigabytes of shared memory. The method adapts to yours. The install guides say, install FastFlowLM, run your model, everything works. In reality, memory allocation errors, process terminated, exit code 1, then the NPU loads, but it's capped at 60% utilization. Nobody explains why. The missing variable is context window sizing. When it's too large, the NPU starves for data and throttles down. Standard tutorials fail because they assume infinite headroom. The root cause is simple. The NPU is constrained by system memory limits. On 16 gigabytes of shared RAM, the context window becomes critical. The NPU waits for data, throttling itself as memory bandwidth saturates. The equation is simple. Context window tuning plus active monitoring equals full utilization. It's not magic. It's reproducible math. Achieving maximum throughput isn't about a cheat code. It's an iterative discovery process. You balance your model's memory footprint with your NPU's constraints. Test at maximum context, observe where it crashes, then reduce incrementally. Find the threshold where the NPU saturates without triggering system swap. F or 5.4 mini on my setup. That perfect threshold is 12,288 tokens. Exactly 12K. Phase 1 started with FastFlowLM's default 32K context window. Result: instability and immediate crash. 16 gigabytes of shared RAM can't hold that capacity. The math doesn't close. The failure reveals your ceiling. From there, you tune downward. Treat context size like a volume knob. Too high, distort. Too low, weak output. Adjust methodically. Phase 2 dropped to 8K context. The model loaded smoothly and stayed stable, but NPU utilization capped at 60%. Safe, but underpowered. The NPU wasn't fully fed. Many stop here because it feels reliable. But for production systems, stability alone isn't enough. Efficiency matters. Phase 3, 12K context. The model loaded instantly and ran fast. NPU utilization stayed between 90 and 100% for over 30 minutes. No crashes, no memory issues. This is the Goldilocks zone. 12K context on 16 gigabytes. It's engineered, not guessed, and fully reproducible. Treat the context window like a tuning dial. Step 1. Identify your failure point, 32K in this case. Step 2. Reduce incrementally, 16, 12, 8. On one end, the system crashes. On the other, utilization drops. The middle zone gives 90 to 100% NPU activity without swap thrashing. That's your sweet spot, unique to your hardware and model. Before running tests, configure your environment. First, initialize Lemonade Server for exclusive NPU access. That isolates the workload. Then, launch Gaia CLI to pass arguments directly. Command line control allows precise context sizing. GUI interfaces often hide these parameters, so command line testing is essential. Here's the working protocol. Test sequence A, try 16K. Watch for lag or warnings. If instability appears, reduce to 12K or 8K. Run a 1-minute generation test. Track performance. When sustained load reaches 90 to 100% and stability holds, lock those parameters. 2 key signals define success. First, failure. The NPU stalls or underfeeds due to memory starvation. Second, success. Sustain 90+% NPU load during token generation. The metric is consistency. High utilization, no crashes, no system swap. On my setup, I reached 98% sustained at 12K context. That's proof of full optimization. Before versus after. Before, default guide, 60% load, crashes, and frustration. After, optimized protocol, stable operation, and full utilization. Remember, shared memory is divided among CPU, GPU, and NPU. Close browser tabs, Electron apps, and background tasks. Every megabyte counts. Different models vary. 5.4, Llama, Mistral. Rerun the protocol each time. Don't trust default settings. They're not built for mobile hardware. Context window sizing is your main optimization lever. Through systematic tuning, your NPU becomes a 100% workhorse. The full guide is on my GitHub. Test it, share results, and let's push Ryzen AI performance forward. Thanks for watching.